Hello, Chem 121 students. My name is Professor Hudson, and I'm going to be walking you through the activity series of metals lab. So let's go ahead and dig in and get started. So first we're going to look at the periodic table and a type of reaction called redox reactions. So here is a nice sketch of the periodic table, and I know you're looking at this thinking like, wow, Professor Hudson, you really could have had a career as like an artist, and I could see this sketch totally hanging up on some sort of art gallery wall, and you would be totally wrong in saying that, let's be honest. Okay, so there are going to be a couple of sketches in here, and I do apologize, I am clearly not an artist. Okay, but let's take a look at the periodic table. So the periodic table is broken into essentially two main regions. So we have the region where we have our metals, and metals are characterized essentially by the way they behave in a redox reaction. So it turns out that metals are oxidized. So the ox in redox reaction stands for oxidation. What happens in oxidation is you have a loss of electrons. So in our example here, we have a metal, which is our free element, so a regular metal, that is going to M plus an electron. So an electron was lost, and we call this process oxidation. Okay, so it doesn't have to just be, say, one electron. This could be a different type of metal, and it can form metal plus 2, for example. And if it formed a metal with a plus 2 charge, then that means we would have lost 2 electrons in that process. Okay, on the other side of the periodic table, we have our nonmetals. So our nonmetals are characterized by how they behave in a redox reaction, and they tend to gain electrons. So in gaining electrons, we call this reduction. So that's the RED part of redox, stands for reduction. So in reduction, we have gain of electrons. So for an example, X, which is any of our nonmetals, plus an electron to form the anion X minus. So gain of electrons forms our anions. Okay, so we could have had, similar to what we have above, let's say X gained 3 electrons. Then we would form X minus 3 as our anion. So it could be 1 electron at a time, could be 2, could be 3. Okay, so again, when electrons are transferred in a reaction, we call this oxidation reduction or redox. So in the reaction itself, we do have electrons transferred from one element to another, and that's what's characteristic of what we call redox. Okay, so let's take a look at a sort of basic redox reaction. So if we want to figure out, one, if something is a redox reaction, and two, what was oxidized and reduced, we need to track the oxidation numbers. So the oxidation numbers are essentially like an electron tally to let us know if that particular element has taken on electrons or has lost an electrons. So for our sort of monatomic ions like we have in this example here, it's pretty easy to figure out the oxidation number. So the oxidation number is equal to the ion charge. Okay, so we're going to go through and we're going to track our oxidation numbers in this reaction between magnesium and oxygen. Okay, on the reactant side, we have Mg solid. So this is magnesium in its free elemental state. So it has an oxidation number of 0. So next species, our oxygen, our O2. Again, even though it's diatomic, it's still in its elemental state, so its oxidation number is also 0. Okay, on the other side, now we have magnesium ion and oxygen ion. They're forming a compound. So now their oxidation numbers are equal to the ion charges. Oh, sorry, that was fun. My mouse kind of took on a life of its own there. Okay, so magnesium will be plus 2, and our oxygen will be minus 2. Okay, so we have gone from oxidation number of 0 on the reactant side to either plus 2 or minus 2 for our magnesium and oxygen on the product side. So let's track our oxidation numbers. So for magnesium on the reactant side, we had 0, so we can put that here. On the product side, it went to plus 2, so we can put that here. Oxygen was also 0, and then on the product side, it is now -2. Okay, so clearly our oxidation numbers changed for both species, so we do know it was a redox reaction. And now we can look at how these oxidation numbers changed to figure out which species was oxidized and which was reduced. Okay, so magnesium went from 0 to +2, so that is loss of electrons. So loss of electrons is oxidation. And then we went from 0 for oxygen to -2. So oxygen gained electrons to become more negative, and that is called reduction. So magnesium was oxidized and oxygen was reduced. Okay, so a way that your lab introduced as a sort of method of showing the oxidation and the reduction process is using what are called half reactions. So oxidation and reduction half reactions. So what we're going to do is break up this reaction into two pieces, into an oxidation part and to a reduction part. So that's what we're going to see right here. So in the top, we have our magnesium, which we determined from above. That was our oxidation process. So we have magnesium metal going to magnesium 2+. So bringing in the coefficients for the reaction, I get that 2 magnesiums are going to 2 magnesium 2+. So in that process, 4 total electrons are lost, 2 for each magnesium. So this is the oxidation half reaction. So down below, oops, sorry, my mouse took on a life of its own right there. Down below, we have reduction. So our reduction process is our O2, so our 2 oxygen atoms taking on 4 electrons to become 2 oxide anions with -2 charges. So what's really important about redox reactions is that they are balanced in a sense that the electrons in one of the reactions has to equal the electrons in the other one. So electrons are lost or transferred in a process if they have some place to go. So magnesium will only lose those 4 electrons if they're going to be taken in somewhere else. So because we have those oxygens that are going to take those in, we do have transfer of electrons. So again, it is important in these redox reactions that in your half reactions, your electrons in one process, say your oxidation process, matches the electrons in your reduction process. So those have to be equal. So in the lab today, we're going to see a lot of metal-metal redox. Our example below is a metal and non-metal, but you're going to see a lot of metal-metal redox reactions. But the process is exactly the same. We just need to track our oxidation numbers. So we have chromium solid, so like a solid piece of chromium metal that we're putting into a copper chloride solution. And the result of this is we're going to form 3 moles of copper solid, so like the metal, and 2 moles of chromium chloride in solution. Okay, so we're going to do the same process from before. We're going to track our oxidation numbers, and we're going to put them in this chart here so we can figure out which one's oxidized and which one's reduced. Okay, let's start with our chromium. So our chromium solid it's free metal, so its oxidation number is 0. So on the reactant side, chromium is 0. Okay, so let's now move to our copper. Okay, so copper is in a compound here, so we know it has an oxidation state that's not 0. So copper in this case is going to be +2, and I know that because each one of those chlorides is -1. Okay, so chloride -1, which makes that copper +2. So on the reactant side, I can put in a +2 for my copper. Okay, let's move now to the product side. So we have 3 Cu solid. So now copper has gone into its free metal state. So now we know its oxidation number is 0. So I'll put that in under copper as 0 here. And then if we look at our chromium, now chromium is in a compound. So we know it has oxidation number that's not 0. So because the chloride has not changed oxidation number, it's still -1. I know that that chromium has to be plus, and that will be a 3. So we can put that over here. Now chromium is +3. Okay, so chromium and copper are the two elements in this reaction where the oxidation numbers have changed. So they are the ones involved in the oxidation reduction process. If we look at our chlorine or our chloride, the oxidation number hasn't changed. It's chloride -1. On the reactant side, it's chloride -1 on the product. So not involved in the redox reaction. Okay, so if we look, chromium went from 0 to +3. So to become more positive, that means loss of electrons. So chromium was oxidized. If we look at copper, it went from +2 to 0. So it became less positive, meaning electrons were added or gained. So this one was reduced. So our chromium is oxidized, our copper is reduced. So the way that we're going to show this in the lab, after you figure out what reaction is happening, is we're going to show what are called net ionic equations. Net ionic equations are really, really nice for this type of reaction, for essentially a single displacement reaction with metals, because it tells you or shows you exactly your metals oxidized and reduced. So let's take a look at writing out the ionic equations for this reaction here. So if we look what was given to us to start this one over here, I'm going to put an M. This was the molecular equation. So the molecular equation shows all of our species, and anything that's aqueous, it's showing it as a compound. But we learned in chapter 4 but that's not really how ions behave in solution. They're not tied together in a compound. They're all free floating. So any strong electrolyte is going to do what we call dissociate and is going to be just free floating ions in solution, not tied together in a compound. So we're going to show this in an ionic equation. So let's take a look. So we have, oh, it looks like my mouse went a little crazy again there. Okay, so we have, I just rewrote the molecular equation. So this one here is still the molecular equation. So I just transposed that over here to give us something to work with. Okay, so our chromium plus our copper chloride to give us our copper solid plus our chromium solution. Okay, so what we want to do in the next step is take any strong electrolyte, so any sort of strong acid or soluble ionic compound, and break it apart into cations and anions. So this is called the complete or total ionic. So that's what we have here. So when I'm doing something like this, I like to remind myself of things that are not ionic. Okay, so this is not an electrolyte. This is a chunk of metal. Okay, so this would be a piece of metal that you could hold in your hand. So the same thing is true with the copper. This is a solid chunk of metal, again, that you could hold in your hand. The others, though, those are soluble ionic compounds. So these would look similar to, say, dissolving salt into water, where it completely breaks apart and is incorporated into the solution. So those are strong electrolytes. Those are what I'm going to break apart into anion and cation. Okay, so that's what we have. So if you see the our solids haven't changed going through the whole entire process here. So copper, 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 and same thing with our chromium. So again, since they're not electrolytes, they're just going to be sort of passed through these ionic equations. Okay, but the important part now is we have to break up those electrolytes. You can kind of think of this as almost like distributing, like we do in algebra. So that coefficient is going to distribute through to your anion and cation. So when we distribute that 3, we get 3 copper ions. And if we distribute this 3 to the chloride, we have a coefficient of 3, but a subscript of 2 as well. So those are going to combine to give us 6 chloride ions. So coefficient of 3, subscript of 2 means there's 3 chloride ions floating around. Okay, so the same thing is going to happen here. The 2 goes with the chromium. So we get 2 chromium 3 pluses. And same thing, this 2 also goes with the chloride, and we end up with 2 times 3, which gives us the 6 chloride. Okay, so that is what we call a total ionic, where we've taken strong electrolytes and essentially broken them apart into ions, which is really how they exist in solution. So the last part to go to our end step, where we're trying to get what's called a net ionic So where we are eliminating species that aren't really actively participating in the reaction to get what's called net ionic. So for this step, we're going to eliminate what are called spectators. So spectators aren't actively participating in the reaction. So for our case here, it's the chloride. And we know that because they haven't changed from one side to the other. There's the same number of them. They are chloride minus. They're aqueous, so their state hasn't changed, their charge hasn't changed, nothing about them has changed from one side to the other, so we're going to eliminate them. So when we do that, in our net ionic equation, we get the chromium solid plus the copper ions to yield the copper solid plus the chromium ions. It's essentially just giving us our species that were oxidized and reduced. And in this type of reaction, when you get to your net ionic equation, that's always what it shows you, your element oxidized and your element reduced. Okay, so how do you know when a reaction is going to happen? So in lab today, you're going to notice that there are going to be some reactions that you're going to observe happening or occurring, and some that are going to yield no reaction. So kind of compiling all these observations, metals were ranked into what's called an activity series. So in an activity series, we're essentially saying these ones are very, very active or reactive, and these ones are not. So how this is read is these ones at the top are the most reactive, which means they're easily oxidized. So I'm going to put an O up here. These ones are very easily oxidized. So what that means is the ones at the top of the list are lithium, potassium, calcium, sodium. These ones are rarely found in their elemental form. Like if we were to go out into the environment and try to collect samples of just pure lithium or potassium, it would be very, very difficult to do. These are very, very reactive. They react with some things that we consider really, really inert, like water, and you're going to see that in the lab today. So those ones at the bottom are the opposite. They're very, very difficult to oxidize. So what this means is you're going to find them typically in their free element state. So this doesn't mean that they're not ever found in compounds. They are, but it's really, really difficult to oxidize them. So they're at the bottom of the list. Okay. So how this is read is I always base it off of my free element. So let's say we had a sample that had aluminum. So let's say we had aluminum metal. So Al solid. And we wanted to oxidize the, oh my gosh, my mouth is really crazy today. So say we wanted to oxidize the aluminum. Okay, so we look at our activity series. Aluminum is right here. So how the activity series is read is that for our aluminum metal, anything below that in solution could oxidize the aluminum into aluminum 3+. So we wouldn't want to choose, say, lithium chloride, potassium chloride, calcium chloride solution, or sodium, any of those up there. So we'll put an X. These ones aren't going to work. Okay, these are not strong enough to oxidize aluminum, but anything below that could. So I could put this aluminum into a solution of zinc chloride or chromium chloride or iron nitrate or nickel nitrate. Okay, so any of the ions below it would then oxidize the aluminum. So you get the aluminum going into aluminum ions, and you'd get the ions in solution, like for example, your hydrogen or chromium, they would be reduced out of solution into their elemental form. So anything below that would work in the reaction. So let's get our color. So essentially anything below that is going to work. Okay, so that's how this one is read. So what are you going to be looking for in your reaction today? So what evidence of a chemical reaction are you going to observe? Okay, so again, you're welcome, my art. So first we're going to look at evidence of metals reacting with an acid. So metals will displace hydrogen in acids. So if you go back and look at that chart, hydrogen was on there. So in a solution, it's an acid, but when it comes out, when it's reduced, it comes out as hydrogen gas. So hydrogen is, in its elemental form is H2 gas. So what you're going to observe today, if a reaction is occurring, is you're going to see the release of the hydrogen gas, which I've indicated in this test tube here with the little bubbles. So it might be completely obvious with this super fast, vigorous reaction where it looks like it's foaming and bubbling like crazy, or it could be a lot more subtle. So I tried to kind of show that down here with my super duper art skills, where maybe you just start to see bubbles forming on the surface of the metal, and then every once in a while a bubble escapes up through the solution. Okay, but you are looking for the evidence of hydrogen gas being produced when we have the metal reacting with an acid. Okay, so evidence of a metal reacting with another metal. These ones are a little bit more subtle. Okay, so again, you're welcome, my art here. So the metal being reduced will start to deposit on the surface of a metal. So in this first test tube here, which I'll call test tube 1, and you can kind of see that, well, how I tried to draw it anyway. So this one here is, say, the metal that was put into each of those test tubes. So that's sort of for our reference. But you can see this one is starting to get some reddish deposit on the surface. That would be the copper depositing on the surface of this metal. So that's something that you're going to look for. Changes on that surface of the metal in solution. Okay, so this one here, this one looks exactly the same as our reference metal. So it doesn't really look like anything is happening here. So this one would be no reaction. So again, our observation for this one would be no reaction. Okay, so this one here, I tried to draw with starting to get dark spots on the metal. So sometimes you get like this, looks like crazy fur growing on it with all that metal depositing. Sometimes it's more subtle, and you'll start to see dark spots forming on the surface of the metal. So that's what we see in this one. This one here is really, really a lot more subtle. So this one here, the metal is just a slightly darker shade of gray. So this one we would really want to put next to our original source metal to directly compare to see if we do see any differences. Okay, so those are observations you're going to be recording on your report sheet, is what changes you see happening on the surface of the metal. So another indication of a reaction will be change in the color of the solution. So a couple of the ions we're using, for example, copper 2 and iron 3, are very colored in solution. So when copper ions are in solution, they make it this really nice teal blue color. So that solution in that test tube is kind of a teal blue color. So looking at solutions changing color is also evidence. So if copper is leaving solution and being deposited, we should see that teal color becoming much lighter over time. If copper is going into solution, we should see the solution becoming more teal over time. So the same is true with iron. Iron 3 is yellow, so we can see a solution becoming more yellow or less yellow as an indication that a reaction is happening as well. Okay, so the last thing to look at is your report sheet. So you are recording your observations today. So the way this works is you're going to fill in your observations in your notebook in these boxes. So as reference, these metals over here making the column, these are the solid chunks of metal. So this is the solid metal. So we're going to actually place these metals into the test tubes. So that's your metal. On this other side here in the rows, these are the solutions being poured in. So we have these sort of X's here. So we're not going to put a solid chunk of magnesium into a solution of magnesium. That's ridiculous. So your first one here, your first box, I'm going to call number 1, we would be observing a piece of magnesium in a solution of zinc, so like a zinc nitrate solution. And then we would observe any changes that we see in the reaction. Okay, so that's how that's sort of read. So number 2, we would put that a solid piece of magnesium into a solution of iron 3. Okay, and we would observe any sort of reaction we would have there. So that's how these go. On the next one again, so this one down here, we'll call it 3. This would be a solid piece of iron placed into a solution of magnesium ions. Okay, so that's how this chart is read, and you're going to record your observations. So what should you be recording? Well, one option is that no reaction occurs. So if that's the case, just like we see in our example, I'm just going to write NR, no reaction. If you do notice any changes, you do want to record those. So if there is a reaction, write down all your observations. Specifically, write down what you see happening at the metal. So the metal is getting darker. The metal has this sort of reddish deposit on it. The metal's turning darker, or anything like that. And second, you can look at what's happening with the solution. So our sort of example here with aluminum, the metal is turning dark, and over here, the solution is becoming colorless. So those are the observations noted for aluminum. Okay, so the aluminum was done for you to give you examples of how you're going to record your data and put it into this chart. Okay, so again, what's happening with the metal and what's happening with the solution. So be sure to number your boxes. So these ones down here aren't going to count, so we're not going to number those, but I have 1, 2, 3, 1, 2, 3, so I'd call maybe this one 4, 5, 6, 7, so on, so on. These ones get numbered down here as well. So make sure you number these boxes also, so that when you go to start writing out your net ionic equations, your instructor can take the number from your box and match it up to the reaction that you wrote out. Okay, so again, these ones down here with the aluminum, you are writing out these reactions. You're not writing out any of these that have been grayed out for you. Okay, so you should have exactly enough lines to cover writing out a net ionic equation for all of the boxes, again, including the aluminum. Okay, so that's essentially it. Make sure, again, when you're watching the video, this is an observation lab, so make sure you're really looking for those bubbles forming or not when you're looking in the acid part. And then when you get to the metal part, again, make sure you're looking for those changes at the surface of the metal. You're also looking for those changes in the color of the solution as well.
All right, this is the sodium-potassium demonstration portion of this laboratory exercise. This is a part that would have been done by our instructor anyway, but because it's included on your lab report and you are asked to comment on your observations, we're going to include it here in this fashion and let you see. So what we're going to start with here is a container that's full of sodium metal. Sodium metal is reactive with water. So just to, here's a piece here. I'm just going to turn the light on briefly so you can see it. Here's the sodium metal itself, kind of not very lustrous. And then it reacts with water, so we're going to put it into water. We're going to observe what we see. Okay? So what you're going to see in this particular reaction is you're going to see the exchange between the sodium and the water as it makes a single displacement. You'll also see the release of energy in the form of electricity. You might not be able to see the heat, but it's going to make the water boil as well. So we're going to put this watch glass up on top just to make sure it doesn't splatter out. So you'll see the release of energy in the form of light. This is one of the old-fashioned ways in which energy was produced before we had the modern light bulb, etc. So without further ado, here is sodium. It's going to take a second to start because it's covered with oil to keep it from reacting with the air. enough, I don't see any light. Sometimes it lights up, sometimes it doesn't. But if you look just below the surface here, you can see some turbidity as the gas is released. Oh, there you go. In the very back corner on the right-hand side of the smaller screen, you can see a little bit of light coming off the sodium there. And it will continue to react until all the sodium is consumed. So it's just a tiny bit now. Now we're going to do the exact same thing with potassium. Potassium is also water reactive. Metallic potassium has very similar characteristics and a similar reaction, although potassium releases a little bit less electricity and a little bit more light. So again, this is just a beaker full of purified water. I'm going to pull out the potassium metal and show you, just so you can see it. It does look slightly different. And then we're going to see the same reaction. You see it's similar, but just a little bit different. And we see a very similar reaction with it. Again, it's covered with oil, so that will delay the reaction just briefly. So we're going to see the same chemical exchange in a single replacement, and we will see the release of energy. I'll try and rotate this one so that you can see it once we find out where it is. Okay. So as you can see, the potassium is a lot more dramatic in terms of its energy release. It doesn't last quite as long. It reacts much more quickly than sodium. And that's it. So that concludes the instructor demo. Please make sure you make your observations of what you saw, and then some explanations for what might have happened in this particular exchange.
In part B of the lab, we are looking at the reaction of different metals with acids. So in this first test tube here, we have our magnesium metal. Next in this one, we have our zinc. Third here, we have iron metal. And then this fourth one here, we have our copper. So to that, we're going to add our solution of 6 molar hydrochloric acid. And we're going to observe if the metal and the acid are undergoing a single displacement or a redox reaction. Okay, so let's do this. Make sure you record your observations. All right, so make sure you record again this first one here was magnesium, got our zinc, the iron, and then we had the copper. So record your observations in your report sheet for part B, the reaction of metals with acid. Okay, so for part C of the lab, we are looking at different metals that may or may not react with metals in solution. So we're looking for single displacement reactions with 2 metals. So in the well plates here, we have all of the metals. So it should look just like it does on your report sheet. So our solid magnesium, for reference, is right here. So all across this row, we have the magnesium pieces. Zinc has kind of a fun shape. Here's zinc and our zinc metal. Iron with our iron metal, and then finally copper with our copper metal. Okay, so then for our columns, this is going to be our solution of metal. So in these wells, we're going to put the solution of magnesium nitrate. So we have our magnesium nitrate. That's going to go in our wells here. So we'll fill it, we cover up the metal. Okay, so we have our first column now with our magnesium nitrate solution. So next we have our zinc nitrate solution. So we're going to fill in here. So moving along, next we have iron. This is iron 3. And finally, we have our solution of copper ions. Okay, so we're going to let this react for, we'll leave this go for a while, and we'll come back and we'll take a look at our metals and see if we notice any differences in solution or differences that we see at the surface of the metals. Okay, so we've left these reacting in the well plates for about 15 minutes. So now we want to take our metals out and compare them to the original. So I'm going to place the metals in sort of their slot here. So I'm going to move these off to the side. And then we're going to place the metals on the white paper so that we can compare them to the original. So this was the magnesium. Oh, here we go. So here's our magnesium, and here's the magnesium now in zinc. Here we have the magnesium metal that was in the iron solution. Here is the magnesium in the copper solution. Okay, so going to our zinc. Here was our zinc in our solution of magnesium. Here was our zinc in our solution of iron. And here is our zinc in the solution of copper. Okay, moving now to iron. Here's our iron with magnesium. Get out there. Oh, buddy. Aha. Here is the iron with the zinc. And here is the iron now in the copper solution. Okay, now moving now to copper. Copper and magnesium. Copper and zinc. And copper and iron. Okay, so here are the metals. So you can now compare the metal that was in the well plate now to the original metal that came from the jar. So note any surfaces or any changes you saw to the metal. So record observations if your metal has changed color. And also as you were watching the video, if the solution was changing color as well, make sure you record those observations.